Welcome everyone. The topic for our presentation is image compression. Introduction of HD quality in space satellite imaging, medical imaging, multimedia, and many such similar fields has led to increase in bandwidth and storage requirements. Example, transmission of an HD uncompressed video of 1024 by 768 size with 25 frames and 24 bits per pixel requires 472 Mbps and approximately 1.7 GB storage for a 1-hour video. Pixel is the smallest addressable and controllable element in an all-point addressable display device. Pixel density is the number of pixels in a square dimension of a display frame. It is proportional to the camera quality. Mathematically, number of pixels decides the size of a matrix. Image is a two-dimensional array of pixels wherein binary image has pixels as bits, grayscale image has pixels as scalars, and a color image has pixels as vectors. Mathematically, image is defined as a two-dimensional function fxy, where x and y are spatial coordinates whose amplitude is called intensity or gray level of the image at that coordinate. The intensity of each pixel is variable. Also, color image is typically represented by 3 or 4 intensity components with red, green, blue, that is RGB.
Compression. The storage size of an image varies in order of n square, where n cross n is the dimension of the image. Color images require 3 times more storage since each pixel has 3 values. The knowledge of redundancy present in the image because of highly correlated adjacent pixel values can be used to compress the image. The true color image, which originally required 11.2 MB for its storage, after compression using JPEG, got reduced to 656 KB. Basis transform. With the help of linear algebra, we can find the coefficient Ci in the change of basis from standard basis, that is the light level for each pixel, to Fourier or wavelet basis. Any Rn column vector in image matrix can be written as linear combination of wavelet basis vectors, which can also be written as x is equal to w times c, where w has the new basis vector as its column and our task is to find c, which is w inverse of x. This explains 1D transformation, but for 2D transformation, we first transform the column vectors by multiplying m inverse, followed by transforming the row vectors by right multiplying m.
Block transform coding. We divide the whole image into smaller sub-images of equal size, preferably square. So we do a 2D change or transformation such that the resulting coefficients in the transformed version have more coefficients close to 0, which can be discarded. The block diagram shows that the source image is transformed using the forward transform, then it is quantized. For the reverse process, we use the inverse transform and get the reconstructed image. Discrete cosine transforms. The process of DCT takes place as follows. The image of size p cross q is subdivided into n cross m, preferably n equal to m. The number of subimages are given by p cross q upon n cross m. For the n cross m subimage, Fij is the intensity of each pixel and I and j are the spatial coordinates. We transform it using the DCT matrix transformation to Fu, v, which will also be the matrix of size n cross m. But as all the natural images contain more energy for the lower frequency part, so the Fu, v matrix will contain more coefficient values which are close to 0 corresponding to the higher frequency part, thus making the compression possible. The general equation for the 2D DCT is as shown, and the equivalent matrix contains the orthogonal vectors. So because of this, the calculation of the inverse becomes very easy, as it is just the scaled version of the transpose. The normalized transformation matrix is unitary. This doesn't change the norm of the vectors from the previous basis.
Wavelet transform. The compression logic in wavelet transform works by processing the whole image and generating 4 sub-images, namely approximation, horizontal details, vertical details, and diagonal details. Since the last 3 sub-images are highly correlated, they can be coarsely quantized. thereby reducing the image size. Moreover, we can also decompose the approximation matrix into 4 subimages as shown here, which is second scale transform. Starting point for the definition of Haar transform is the Haar functions which are defined in the closed interval of 0 to 1. The corresponding 8 cross 8 transformation matrix generated using these basis functions can be represented as follows. It is not difficult to see that H inverse is equal to H transpose, that is H is unitary and it is not symmetric. The following example depicts the lossy image compression technique for an RGB image. To obtain a better quality of image with less compression, JPEG allows us to choose a number close to 100. In this image, we can see how the error gets more significant as the chosen number for the quality decreases. For quality 1, one cannot fail but notice the image hidden inside the error matrix.
To conclude, we can say that the selection of a good basis matrix depends on the time required to invert that matrix or to multiply by its inverse. The selection also depends upon the final transformed matrix. The more the number of CIs with small values, the better. The best transformation matrix will be the one which consists of eigenvectors of the image, so the transformed image will be a diagonal matrix of eigenvalues. Thus, using image compression, we can save a lot of memory which can be used for other purposes. Thank you.